Okay, great. So let's get started, I would say. So let's see where we are now. So we are in part 3. So yesterday we left off. We were talking about neural networks and how they died. We were talking about their fall in around 1960. Yeah. Now, today there has been a rise of machine learning and neural networks in particular. I wanted to start by showing you some memes, which I think are very, very true. I mean, they're not just jokes. Do you remember the 10 years challenge? So
yeah,
people were like showing pictures of of themselves 10 years ago. So I find this one really funny. So yeah, in 2009, people were talking about this as statistics. Now, this is called machine learning. And you can find all sorts of memes that are similar to that one. And yeah, I kind of agree. I mean, it's applied statistics in the end. I mean, machine learning is applied statistics in the end. I think somebody argued that there is a difference, but I'm not really sure which one is that. But anyway, so clearly, I mean, we don't have the time to talk too much about maths in this course, especially because machine learning relies on a really wide set of tools, from calculus, probability theory, statistics, and geometry, and so on. So we won't really dive in details today. I'm just gonna give you an idea of how machine learning works, what are its main fields, and what it is really, what its risks are, and so on. So already in 1959, Samuel defined it as the subfield of computer science that gives computers the ability to learn without being explicitly programmed. So he was talking about using data to answer questions about something that we haven't seen in the data, that is not in the data. So we train some model, and we want to use that model to make some predictions. So, for example, yesterday I was looking at, I was thinking about a nice example for this. And I thought, well, bridges are kind of a very, very varied type of building, right? Because you can find all sorts of bridges all around the world, and they look very different from each other. And so this is why sometimes it's very difficult for a machine, or it used to be very difficult for a machine to tell whether a given picture has a bridge in it or not. For example, like in this picture, we see a bridge from below. Here we are on the bridge. This picture is taken up at night. So there are many problems that actually are difficult to address just using rules, in a way, which is what logic does to some extent. So yeah. And then I also noticed that somebody else captured this image of a CAPTCHA. I'm sure you all know what it is, which is a mechanism to tell whether an entity is a machine or a human. And yeah, they were using bridges. So yeah, bridges are so varied that they can be used as a test for humanity, if we want to say so. So yeah, so yesterday we talked about the fall of machine learning. Today we're going to talk about why machine learning has now having a rise. The trend, the popular opinion nowadays, if you look at the news if you listen to the radio, is that basically these three things are actually the same thing. So this is what, at least what people, I think, non-experts perceive. So this means that, I mean, machine learning has become very, very popular. And it regained attention starting from around 2010, I would say. Why? People were talking about machine learning already in the late 50s. And I think there is a variety of reasons here. So, for example, the fact that big data, we have incredible amounts of big data, and all these techniques require an incredible amount of data for training sometimes, especially neural networks. This data can be stored at really low costs. There are some new powerful technologies that do basically they multiply. They are specialized for multiplying matrices. So, for example, GPUs and TPUs. And then there is also this rebranding as deep learning that sounds so cool. I think all of these reasons are part of the big picture, right, of the answer to this question, why. So what I want to do is to talk about the three main types of problems that are tackled by machine learning, plus one. Well, I'm not going to talk too much about this. Probably tomorrow we'll have more room to discuss this. But people is talking, we're talking about especially these three types. And so types of machine learning that involve some form of quantitative uncertainty. Can you hear me, by the way, because I have a bad network quality message here. Can you hear me well?
Yeah, there was just a brief interruption, but now it's okay.
Okay, fine, because I can fix that if I can try to fix that if it's too bad. So supervised, unsupervised, yeah, people used to think about that. So supervised, unsupervised, and reinforcement learning, which is based on some form of quantitative uncertainty. But then I would say it's important not to forget that machine learning is also can also be non-probabilistic. So there exists also a form of learning which is logic-based, and we will. I will show you relating to this. So, have you ever heard of these three terms before? So, supervised, unsupervised, reinforcement. Is this the first time you see them, or?
Yeah, for me it's the first time.
First time, okay. So what's the point? So these are three very different tasks. One is so supervised learning. Supervised learning learns from labeled examples, which means I give you, so I have an algorithm, which you may think of as a black box. And I ask it, for example, to classify this image. Does this picture contain a bridge or no? And let's say that the machine says, no, there is no bridge in this picture. And then I give you the label. So I give you the correct answer. I tell the machine, no, machine, you're wrong. There is a bridge. It's here. You might get confused because there is another object which looks like a church or something in the picture. It's taken at night, so it's really difficult to tell. And then I ask the machine, well, now that I've told you this, I want you to learn from this. So try to acquire some new information. And the really impressive thing is that if I provide the machine with a lot of labeled examples like this one, so a lot of pictures of bridges, it can reach really high levels of accuracy. So it can really manage to distinguish, to decide whether there is a bridge in a picture very accurately. Okay, and this is why people are sometimes so impressed with machine learning. But in this case, in the case of supervised learning, we are assuming that we are giving the machine the data, but also some sort of label associated with that label, with that data. So some techniques, just to give you the names of some popular techniques. So we have support vector machines, which are very basics, although the name sounds a bit, sounds really, really difficult in a way. Then we have naive Bayes, which is what Heikel was talking about, the Bayes theorem in the first lecture. And what naive Bayes does is precisely, so given that we have labels, it exploits the knowledge of some label associated with some data to update a probability function in a naive way. This is why it's called naive Bayes. So this is why Bayes theory and probability theory in general are important for machine learning. I mean, this is not the only place here where we have Bayesian statistics, but this is the most straightforward application of Bayes theorem to machine learning. So I thought that was worth mentioning because it's something that you've already seen. Oh, sorry, I've lost my secondary monitor got disconnected. Just give me 1 second though. I need to plug it in again. Oh gosh, sorry. This connector is, I call, flimsy. You can still hear me, right? I don't know what happened. Ah, okay. Okay, I'll need to reshare the screen. No. Okay, so can you see the presentation again?
Yes.
Okay, great. Sorry. So I was talking about naive Bayes, I think. Then we have these, well, these two and this other one. No, especially about these two, we're not going to talk too much. But there are also methods used in machine learning for supervised learning. And then we have neural networks, which, as we saw yesterday, they are based on the McCulloch and Pitts model. We will see an example in a second. And K nearest neighbors, I think we will see an example in a few slides as well. So let's assume that the wrong resolution. Okay. Okay, this is better now. So let's see that there is a bird that has to decide which one of these objects to eat. Okay. Well, since I'm Sicilian, I would, if I was a bird, I would personally eat an arancina. But anyway, I assume that the bird prefers the blueberry. So let's go back 1 second to the McCulloch and Pitts model we saw yesterday. This is something that they were thinking about when they were creating this model. So let's think of this as a neuron that is somehow connected to the bird's eye, right? And then let's say that X1 is an input that detects the roundness of an object. So we have X1 if the bird sees a round object, and X1 is 0 otherwise. Similarly, we have that X2 is a purpleness detector. So X2 equals 1 if the object is purple, X2 equals 0 otherwise. And we want this neuron to fire whenever the bird sees a blueberry. So what do? Let's say that we want to simulate the process of learning, right? So let's say that our bird has initialized this neuron with a random threshold. Let's say that this threshold is equal to 0. So we see pesto pasta, and actually the threshold now fires because the threshold is 0. So it basically fires, it always fires. However, we expected output y1 equals 0 because we don't want to eat pasta pesto, right? So we are basically comparing y1, so the output we get with the expected output of y1. And we conclude that this neuron is too permissive, so we increase the threshold. And this is a very simplified form of learning, right? Because then we might want to say, well, let's increase the threshold. Let's say threshold now equals 1. The bird sees an arancina. Again, we must increase the threshold. So let's say that we increase it too much, so that even when we see a blueberry, we don't eat it. We have to decrease the threshold. So there is a sort of mechanism that allows us to update the threshold, which is very similar to a learning mechanism, right? So this is at the end what we expect the neuron to do. And actually, this is a pretty realistic example, because the actual neural networks behave exactly like that. So modern neural networks that are used for similar tasks. So for instance, classifiers that have to classify bridges, for example, have this form. So they are just neurons that are connected to each other, and usually they have this form. So they are organized in layers, so one can have a very complicated input. Here we have only three characteristics of the input data, and we output a single output y, a single number y. But these are usually real numbers, and so is the output. The usual rule is that all neurons at some level cannot be connected to each other within the same level. They can only connect to the next level. And actually, usually we assume that these, so each neuron in a level has all possible connections to neurons in the next layer. Okay. These connections usually have weights. So it's slightly more complicated. The threshold mechanism isn't really a realistic one. Let's say not anymore. But they take all the inputs, they weight them, and then they output something that depends on the sum of the inputs. Okay, and for each neuron, we have that both the input and the outputs can be real numbers. Okay, the idea, the great idea, which is one of the ways these neural networks are trained. So they learn how to classify data. Is obtained by comparing y, which is the actual output of the neural network, with with our label. So we are still under the assumption that we have labels because we are talking about supervised learning. So if we consider the difference between the output of the neural network and the let's say with the expected output, so the label, we can just go back from the last layer of neurons, go back and try to adjust the weights of our model, so that the output of this neural network kind of gets closer to what we would expect. Okay. And then we repeat the process. So now we know what's the expected output, sort of, for each one of these neurons on this layer. And we can train these neurons. And we do this layer by layer until we reach the beginning. So this is why it's called back propagation, because we go from the output, we compare it with the solution to the problem, let's say, and then we feed this information backwards. Okay. Any questions about this? That is unreasonable. So if it's okay. Oh yeah, so and this also illustrates a main difference between what's usually called a shallow neural network, which only has one hidden layer. So it means that between the input layer and the output layer, there is only one set of neurons in parallel. When you hear people talking about deep learning or deep neural networks, they're just talking about neural networks that have many layers. So there is usually there are many layers here in the middle between the input and the output. And if you want to play around with these ideas, I think this is a nice starting point. I don't know why I clicked on something. Okay, sorry. So I wanted to visit it. Can I open with Safari? Yeah, because I can quickly show you. So this is a website that allows you to play with neural networks. So this is the data that you want to classify, and you give it the answer. Do you see this, by the way? Or are you still seeing the presentation?
We are seeing the website.
Okay, that's great. So so there are two. So in this case, we have a neural network with two hidden layers of neurons. I'm not gonna go in detail here, but anyway, I can add or remove layers, and I can play around. This is the thing that I want to learn how to classify. These are just points in a feature in the feature space. So in a geometrical space. And I the neural network to learn how to distinguish the orange dots from the blue ones. And well, I can play around with the parameters of this. And if I run it, you see that fairly quickly it learns how to distinguish to tell the orange area from the blue one. But if I decrease the number of hidden layers and I decrease the number of neurons, you will see that now the neural network is not as it was before, and it's solution isn't as good as before. Okay. So these things really need a lot of units in order to weigh to work. Okay, this is how they're, and it gives you a nice overview, I think. But anyway, let's go back to this. So another problem. Oh yeah, sorry. So what we were talking about is classification. So we have points in space in this case, and we want to classify a new unlabeled instance. This is an example of supervised learning, because we know that all of these are triangles, all of these points are squares. What do you expect this to be? A very pop called considers the three closest, for example. You can make it larger. You can consider the four closest or k closest points to this one. And then it says, well, within this this radius, or well, the three closest ones are triangles. So I'm going to label this as a triangle. This is a supervised learning technique, very popular. We also have another type of supervised learning type of problem, which is regression. So given a set of points, so these points correspond to some data, to some observations. How do we extract from this a general law that allows us to predict unobserved instances? So for example, for x equals 6.5, the expected y should be around 30, according to this model. But then again, we have a problem here, because we have to find what's the best model that fits our data, and so on and so forth. So you can imagine this is a massive field in itself. So now let's talk unsupervised. So unsupervised learning is the case where we don't really have a desired output. So we don't have labels associated with our data. We only have plain data, and we want the algorithm to learn something about this data. So some I don't know, regularity, some pattern. We want to discover something about this data. So an example is, let's say that I want to sort out my bookshelf. How should I book together my books? I'm not telling you anything else. So I'll just give you, a set of features associated with these books. So the author, the year, the I don't know, publisher, topic, and so on. But then I want the algorithm to find which books are closest to other books and which are not, so that I can separate them into different groups. Without telling you this, for example, this book is a, I don't know, is a romance book, or is a thriller book. I'm not telling you that. I'm just asking the machine to sort it out itself. And this is an example, right? So in this case, we have 3 big chunks of data, and according to these techniques, to this specific technique, the best way to separate them is this one. You can already see that probably you would have separated them in a different way. So again, one must be really careful in choosing the right technique for different problems. But in this case, we get this. So this is the outcome of the. This is called clustering task. So it's dividing the data in these 3 clusters. You may think of better ways of doing it. So that algorithm is known as k-means. There is another algorithm that is really useful for. I mean, sometimes these things are mixed together. They are used at the same time, which is called principal component analysis, but we're not gonna go in detail. I wanted you to cite something that I've been working on. So for an explainable AI task that we're gonna talk more about this later on, we scraped a list of recipes from Giallo Zafferano, which is a popular Italian website which collects together recipes, and then we applied 3 means, and we got something like this. So you can see that the algorithm managed, without any intervention on my part, it managed to separate out I would call this secondi piatti, so meat and fish dishes. So we got a cluster with all these type of things, a cluster with all types of pasta, so primi piatti. And then we got a cluster which was very mixed, to be honest, which was more or less, I don't know, side dishes, many things with vegetables. So anything that was vegetables ended up in the 3rd cluster. So this is so we just run an algorithm on a data set that had some features attached to recipes, and the algorithm just sorted out itself the whole the 3 clusters. Okay. Now the last one is reinforcement learning. So reinforcement learning is it takes inspiration from the theory of positive and negative rewards, which is something popular in psychology and, well, neurology as well, I assume. I got this picture from Wikipedia, I promise. I don't know why they were using just pen and paper to represent this, but anyway, it's just like eating chocolate, right? So you eat chocolate, you get, your brain releases dopamine, so you get a positive responding to a positive experience, and then this feeds back into your you want to eat more chocolate, right? And you do that forever until you probably die, or you get fat. So, or well, until you get a negative reward. Can you hear me?
Yeah.
Or am I cutting out too often?
No, we can hear you.
Okay, that's great. So, so this is the basic idea behind reinforcement learning. Why is this important? Why is reinforcement learning important? Because recently, it's proved to be incredibly powerful. So I don't know if you've ever heard about these three things. So AlphaGo, AlphaZero, and Lila Chess Zero. They are really powerful reinforcement learning algorithms that managed to beat one of the world grandmaster in so Go players, Lee Sedol. And why is this nice? Because I think this is a good answer already to the argument from various disabilities that we saw yesterday. That went like, I grant you that you can make machines do all the things that you have mentioned, but you will never be able to make one to do X. So people used to do to say, well, I will never see a machine beat a human chess grandmaster, but that happened in '96. I'm sure you've heard of the great match, Deep Blue against Garry Kasparov, a Russian grandmaster. And well, Deep Blue was mainly based on classical AI techniques. So it was more of a logic-based AI system. But then people said, oh, okay, yes, I grant you that you can make machines do chess very well, but you will never be able to make one that does Go, because Go always seemed to be a really complicated game. So a game that required really considering too many possibilities. So people used to think that there was no algorithm that was able to play Go. So when we were talking about Turing machines being conscious yesterday, I mean, sometimes we hear people saying, well, you will never be able to make machines that can be conscious, but I mean, who knows? There are impressive results. There are machines claiming that they are conscious already. I don't know if you've ever heard of GPT-3. That was was recently bought by Microsoft, and it's impressive. It can write texts about any topic, basically. And he wrote a short text in which it says that it is conscious. So who knows? Maybe one day we will be able to create machines that are conscious, and we will be able to prove they are to some extent. On the other hand, reinforcement learning has proved to be very, very strong, even against classical AI algorithms. So if we, again, consider chess, there is a really strong algorithm that used to be the world championship, the world champion, Stockfish. I'm not really good at chess, but I like it. So sometimes there is a website called PCEC that hosts the world championship of computer chess, and AlphaZero, which is this it's Google algorithm, learned how to play chess from scratch, which is the zero part of its name. So zero means it learns how to play chess from scratch just by playing against itself again and again and again. And every time that it wins against itself, it gets a positive reward, right? So this way, in just 9 hours, AlphaZero was trained as to beat the strongest classical AI chess program out there, which I mean is, I think is seriously impressive. And so these, I can't really go into the details of the mathematics behind all of this. But these techniques usually build upon the concept of a Markov decision process, if you want to check it out. And yeah, the most basic ones are called Q-learning and SARSA. They're not really difficult to. I mean, grasping the basics of these techniques is not very difficult. So you might want to have a look at them. What they do is try to find the best policy. So given a state of the world, what is the best action to take in an environment that given an environment that is, so assuming that the agent is in state S in his environment, what is the best action to take in that situation? So, and it learns by trial and error, just as simple as that. And it collects positive and negative rewards as it goes along. Obviously, you may have really bad negative rewards. For example, if the machine wants to, I don't know, do something really dangerous for its health. I don't know. In the case of automated driving, it might want to drive into a tree. Then you give it a really bad negative reward. Whereas in other cases, you can give it a small negative reward or a positive reward for going successfully, so driving successfully to destination and so on. So yeah, feel free to check them out. I think this is really the point to introduce now the need for an explanation from these algorithms. Why is that? Well, I'm sure that you've all used Netflix. I had collected some screenshots during the last weeks where I was so I was taking pictures like this one, where I was offered an explanation for some suggestions, let's say. So we like being explained things in general, right? Unfortunately, I lost some of these screenshots because I deleted all the content from my downloads folder. And I realized that yesterday, but anyway. So I don't even watch Modern Family, so I don't know, somebody else has done that, probably my sister, but anyway. So I'm getting this explanation. Why? Well, because I will get the reassurance that these films or series are similar sort of to that, so probably I will like them. Okay, and so I'm gonna trust this suggestion. So this is one of the reasons why we need an explanation. Something else I wanted you to something else I wanted to show you, if I manage again. Sorry. Okay. It's a YouTube video. So let's go back to this. So I wanted to, can you see the video? Well, at least one image.
Yes.
Okay, that's great. So basically this algorithm, I'm gonna run it. I'm not sure you will be able to see it because my my connection is really rubbish. So this algorithm tries to invent a prototype of a car that gets as far as possible. Okay, and it starts with some simple cars. It is based on a technique called genetic programming, and then he tries to make them evolve in a way. So each one of these cars has something in common, let's say, with the previous one. Okay. This way, you can see that we get better and better results as we go on. Okay. So okay, let me. I don't know what you've seen really, but this one is kind of good. It's getting far. Yeah, it's managing. So if we skip to the last one, the last one is really good. The last one has learned how to go through the track. I don't know if you can see it very well, but it got stuck at some point, but it managed to unstuck itself. And then I think it reaches the end of the track. So I'm gonna stop this now. The point that I'm trying to make is that would you trust a car that was built this way? By just evolving at random. Well, sort of random, let's say controlled random. I mean, I guess the point is it depends. So these all these algorithms are very good. So they produce really good results, even neural networks. But I mean, would you trust them under all circumstances? So for example, if they are doing safety critical tasks, would you actually trust them? So some people are not really happy with these machines because these algorithms really are black boxes. Okay, so for this reason, sorry, Paolo, I included this here, but the European Union from 2018 has started enforcing this this regulation, the GDPR, which has one part that's called the right to an explanation, that says that basically subjects who have decisions taken on the basis of algorithms that may produce legal effects must be given well, they have the right not to be subject to a decision. Sorry, which may include a mirror. Okay, sorry, I cut out the interesting part. But anyway, we will read it tomorrow when Paolo is also here. The idea is that everybody owes an explanation from these algorithms. So if you can't really get an explanation from these algorithms, then you can challenge that decision and you will always win, according to the GDPR's right to an explanation. Do you think that's fair? Because it's I might be tempted to say, well, yes, it is fair, but in the end, I mean, people don't really. Sometimes they act without really knowing the reasons behind a decisions. I mean, I can myself take a decisions, and I might be affected by some really complicated psychological or biological phenomena. So I mean, why would you apply that to machines? So many researchers said that this is completely unfair. And well, I think there is room for debate here. And I'm going to give you an interesting example. So this is one of my favorites. So there was an independent journal that some journalists dived into COMPAS, which is an algorithm that was used in America to assess the probability that a criminal would reoffend. Okay, and people have used tools like that for a long time. It's scary how many people use these things. And they analyzed one of these. So they analyzed COMPAS, which is one of these risk assessment algorithms in use. So and basically what they found is that black defendants were far more likely than white defendants to be incorrectly judged to be at higher risk of recidivism. While for white defendants, it was the opposite. Okay, and why was that? There was a massive case around this. You can go to this website, which has a link to the dataset itself and to the analysis and to an informal article about the whole thing, the whole machine bias thing. And I mean, it's impressive. Actually, let's see if I can open it. Open with Safari. So, okay, I'm not going to ask you, but I'm assuming that you can see this. This is the website where you can download the actual data from. And then you have here, you have links. So one is about the story. So it's just a journal article. Then there is a methodology article. I'm going to show you that. You see, it's quite a long-winded and complicated article that involves understanding statistics and analysis and things like that. So they were looking for any types of biases, really. So even male against female, white against black, and so on. And at the end, they concluded that there was a higher risk of violent recidivism, but that didn't quite match reality, because so yeah, this is the sentence I'm talking about. Yeah, so there was a strong bias, but what happened in reality is that many people who were classified at high risk didn't reoffend, and then people that were classified as low risk did reoffend. So this was a kind of a big deal in 2016. So there was a hurry to try and find techniques that would explain the results of algorithms coming out from classification, for example. So people came up with this idea, which is one of the most popular ones, LIME, which is short for local interpretable model agnostic explanations. And so the aim of this technique is to carry out an analysis that is similar to the one that ProPublica had to do in the case of the COMPAS dataset, without having to do all the work by hand. So they were thinking, well, we have, let's say that we have an algorithm, or if I switched to another view, but anyway, so they had to, so in the case of COMPAS, they had to do all this work by hand. And they were thinking, well, let's try to invent an algorithm that I give it a simple a black box method for classifying things, for example. And then that method, LIME, in this specific case, gives me an explanation. So we're talking about cases like this one, in which we have many pictures of wolves and huskies. And then we have, well, in this case, we have predicted wolf. We were actually expecting wolf. So we are in the supervised learning case. Well, in 5 out of 6 cases, this algorithm that we used for classification was pretty accurate, we would say, right? I mean, 1 out of 6 is fair, 1 error out of 6. So we could, well, we're fine with this. We are fine with this classifier. So whatever algorithm classified these images seems to be working quite well. So they came out with this idea of a local explanator. The maths behind it is kind of complicated, so I'm not telling you about it, but I want you to take a look at the output. So this is an actual example. So we have this image, which is fairly confusing because we have a dog who's playing the guitar. But anyway, Google predicts electric guitar, acoustic guitar, and Labrador. Okay, so these 3 labels. So we asked Google, tell me what it is in this picture. And Google says, there is an electric guitar, there is an acoustic guitar, and a Labrador. So using LIME, we can highlight the specific pixels that led to these labels. So electric guitar, according to LIME, was given because the neck of the guitar could be that of an electric guitar. I mean, it's actually fairly difficult to tell that this image, so these pixels alone do not really are not sufficient to show that this is a classical guitar. But then we want an explanation for acoustic guitar, and then LIME says, well, Google classified this as an acoustic guitar because of these pixels. And we can see that this makes sense. So Google's decision was sort of correct, right? Because he was, so Google was basing his decision on the pixels that are relevant to the concept of acoustic guitar. And then finally, we have Labrador. And these are the pixels that are more significant to this concept. So, I mean, of course, the authors of this paper argued that these are explanations. An explanation, of course, is a bit more than that, I would say. But I think it's a good starting point. And I would like to highlight that LIME even works with texts. So for example, if you have a text and you want to classify it, for example, you want to classify the genre, you can make it automatically, and then line will give you an explanation of why it was classified that way by telling you the words that the classifier took into account the most. Okay. Now, if we go back to the Husky Wolf problem, it's really interesting because apparently that classifier that we saw was classifying things based on the background of the picture. Because if we go back to this, you can clearly see that wolves always have a white background, and huskies always have a brown background. So the classifier that was doing this task was classifying wolves and huskies according to the wrong principle. So it was simply a snow detector rather than a wolf detector. And so this is why we must pay attention to explanation, I think, and why they're really interesting. So, I told you at the beginning of my part of the module that there is a fourth set of tasks, let's say, we can tackle, or well, techniques that we can use, and these are non-probabilistic, and in particular they are logic-based. Two of these are probably the most famous one is Aleph, which is based on Prolog, and it's been used quite a lot. More recently, which is very powerful, it has very powerful syntax, and it can learn really interesting things. It can even learn preferences of users. And the interesting thing is that it can learn theories. So it can learn axioms from data sets, especially when these data sets are small. So when they are small enough. And given the, logic is really good at generalizing from small data sets. So these methods are really good for learning and generalizing from few examples. Whereas, for example, neural networks are particularly good when you have loads and loads of data. And moreover, they are transparent, so they can tell you why then you are taking decisions based on these methods, because they build theories, and then these theories, which look pretty much like what Paolo showed you, can be used to produce explanations. Okay, they can provide quite commonsensical explanations for decisions. So to finish with, I just wanted to show you a small example. So let's say that we have a knowledge base like this one. So I want to show you an example, a qualitative example of what these algorithms can do. So for example, let's say that we have a knowledge base that tells us that dog, cat, and bird are animals. And then that dog eats cats and cat eats bird. Okay. And then the typical situation is the one where we want to learn from an expert of the field. So we ask a farmer, which animals would you like to own? And the farmer says, well, I would like to have a dog and a bird rather than just having a bird. But then he says, well, but I would prefer the case in which I have a bird than that in which I have a cat and a bird. And he starts giving us information about this. So information of this form. So I prefer this set to this one. I prefer this set here. Sorry, this set here to this one. And so on and so forth. These algorithms are such as Aleph, for example, are able to learn the theory that leads the farmer to pick one set rather than another. So, for example, we can, I don't know if you like, tomorrow we can look at a very simple example where we tackle this task, and we end up concluding that the farmer likes to maximize the number that she or he owns, but the owned animals shouldn't eat each other, which is a theory. So at the end, I can take, I mean, what we've learned has a really natural translation into natural language. So I think it's a really nice and powerful technique. And yeah, if we have the time, we will talk more about this tomorrow.